And thanks everybody for joining again today. So we're gonna, got it. We're gonna continue where we left it off the other day. So that's, if you remember, okay, so the thing that we ended the lecture with yesterday was this completeness principle. This idea that we derive in some special cases out of no global symmetries, and that let us conclude that in any quantum theory of gravity, every possible charge is a physical state on the spectrum. And so, whenever one gets a new conjecture, it's like getting a new toy. And so you want to work out what the implications for this one is. And so this one actually has very interesting, very interesting implications. So, for instance, somebody asked yesterday. I forget exactly who. Sorry, let me just close this thing. I forget exactly who, but somebody asked about what are the implications of this conjecture for the standard model. Well, it does have some implications. Okay, so when one first learns the standard model, one learns about the different fields, right? So, for instance, there's the electron, the quarks, and the whatever. But once one takes into account that the standard model gauge group is SU3 times SU2 times U1, fields must fall in representations of this group, and so that groups some of the fields in the standard model together. So, for instance, you have what we call the right-handed electron, which is charged under just U1, and we have the left-handed lepton doublet, which contains the left-handed electron and the neutrino. Okay, and we have the quarks. Okay, and the quarks they have three components, right? Because they are part of SU3. So you could say they are three component objects because they're in the fundamental, in what we call the representation 3 of SU3. But they'll have some hypercharge, some number here associated to the hypercharge. So they're charged under these two guys. Okay. And when you work out what is the actual electric charge of the quarks, okay, of quarks, it comes out to be plus minus 1/3, as you may know. And this is good because, for instance, a proton has 3 quarks, so it has an electric charge of 3 times 1/3, which is 1. Okay, now this is all high school physics even, but have you ever wondered why on earth did anybody choose conventions such that the electric charge of the quark is 1/3? I mean, who did that? You can certainly change the charge quantum. You could say instead of saying that the electron has charge 1, so the electron you say has charge 1, but you could say instead of that the electron has charge n. Okay, and then you multiply and then if you do this, the charges of everything are multiplied by n. So why do we believe? So why did nobody just say? So, for instance, in this normalization, the charge of the quark is n/3. So why not take n equals to 3, so that the charge of the quark is an integer, and the charge of the smallest particle that we found with the smallest electric charge, which is the quark, is an integer? Why don't we do this? Isn't this weird? Has anybody ever wondered about that? Okay, so I wonder about this a lot when I was first learning these kind of things, and I actually learned a semblance of an answer coming from Swampland. So here's the thing. The reason why people assign charges to the quark to be 1/3 is because quarks are not really particles, asymptotic states, stuff that you can observe, okay? So the idea is that if you have a quark, for instance, up quarks, this is a proton, UD, this guy, which is inside of the proton, has charge 1/3, but you never, ever, never see quarks in isolation. Okay? This is a phenomenon called confinement. It's one of the most important questions in case theory to prove that QCD, the theory that describes color interaction, is actually confining. So to prove mathematically that this happens, okay. The reason why it doesn't happen is because if you try to take one of the quarks out, try to take this D quark out, like here, you can try to put it here. It's connected to the rest of the proton with a linear force. It's kind of like a spring. It's a linear force like the one you have for a spring. And so once you separate it long enough, what happens is that you nucleate a quark anti-quark pair, and then this quark falls back into the proton, and these other two guys form a different particle, which is called a meson. So you never see quarks in isolation, okay? And because we don't see quarks in isolation, people think, well, you know, it's okay to give a fractional charge to anything, something we don't see, we never see actually. It is true in the standard model, every particle that we observe has an integer quantized charge. You could think of the quark as a fiction that we use to understand physics, but there's not really in a standard model, there is no free particle with charge with charge 1/3. Okay. I think this is somebody unmuted. It's Mehdi Sadeghi. Yeah. Can you mute them, Mehdi? Okay. So there's a free particle with charge 1/3. There's no free particle with charge 1/3. Well, here's the thing. If the standard model gauge group is indeed SU3 times SU2 times U1, as you see in Wikipedia, and if you believe the completeness principle, there has to be particles in every possible representation. And indeed, the representation 3 Q electric charge 1/3. So actually, let me, instead of using the full standard model group, let me reduce that to just the color part plus electromagnetic. So this is after Higgsing. You get this group. And so states are introduced, states following representations of both SU3 and electric charge. So a state with charge 3 and electric charge in the representation 3 1/3 is certainly allowed. It's a valid representation, and completeness predicts we have a particle in that representation, like the quarks. But also, this state is a valid representation, and also this one is a valid representation. Okay, if this one is here, then these other two are valid representations. I can construct the Wilson lines we were constructing yesterday, these are the two representations. So if the standard model group is this one, or equivalently this one, then Swampland predicts these particles must exist. Okay, so Swampland is predicting new particles. It's predicting a particle with fractional charge 1/3, and a particle which has the same color charge as a quark, but has no electric charge. These particles have not been observed. We don't know if they're there. Okay, and so you could you could say this is a prediction of Swampland. And you know, if this prediction is correct, then indeed it will be a bit weird to normalize the charge of the quarks to be 1/3, because this would be a free particle with charge 1/3. Now, Swampland tells you, the completeness principle tells you that these particles are there, but it doesn't tell you its mass. So that's, it's not incompatible with observations. This would be, for instance, this one would be an electrically charged particle, which would be extremely heavy, and we wouldn't have observed it. I'm saying it would be extremely heavy because Swampland doesn't say anything about its mass, and we haven't observed it experimentally. So this is probably.
Excuse me, I have a question.
Please.
Are these particles fundamental or a composite of multiple of quarks?
Right. So this particle that I'm constructing here cannot be constructed out of quarks. Okay. So I don't know. So the notion of fundamental versus composite is in itself not very fundamental. For instance, the electron looks fundamental, but in string theory is probably some string oscillating one way or another. Okay. So this particle could be composite in the same way. Maybe it's a string state, or maybe it's point-like all the way to the Planck scale, and then I would call it fundamental. But it most certainly cannot be constructed out of quarks. Okay, when you try to construct particles out of quarks, it always happens that if you have something which is a singlet on the SU3, like here, this thing is a singlet on the SU3, then its electric charge is always an integer. And so that's why this one cannot be produced. Okay.
Okay, thank you. I compare it with quantum Hall effect, where electron is effectively rational.
Exactly. It's very similar to that, but those are, yes, that's right. But those are that's right. Those are composite excitations. They're at no point really you can see a fundamental particle, or you cannot isolate these objects. So they behave as they have electric charge 1/3, but they don't really. You cannot surround one of the excitations in the quantum Hall effect by Gauss's law and measure a quantized charge of 1/3. With this one, you can. You can just put it in a lab and measure it. Okay.
Okay. Thank you so much.
Okay, so I just told you that Swampland predicts this particle, which would be great, but unfortunately, things are a bit more complicated. We are not quite sure that this prediction goes through. This prediction goes through if the standard for sure goes through. Swampland predicts this particle if the standard model gauge group is this. Okay, but actually, we don't know if this is the standard model gauge group. And then you might say, what? But we have measured this at LHC, we've measured the Higgs. So what's going on? What are you talking about? Well, what we measured at LHC, we've measured gauge bosons. We certainly have seen gluons, which are gauge bosons for an SU3, the algebra. We've measured Ws and Zs, which are gauge bosons for U1 plus SU2 algebra. Okay, but measuring, so we know for sure that the Lie algebra of the standard model gauge group is SU3 plus U2 plus U1, but there are several different groups with the same algebra. So in part, actually, what we know for sure is that the standard model gauge group is SU3 times SU2 times U1 divided by gamma, where gamma is a discrete subgroup of this group. So you can take the whole group and quotient by a discrete subgroup. That won't change the algebra, but it will change the global structure of the group. So this gamma, we don't know what it is, but based on the properties of the particles we observed, we know it can be either 1, Z2, Z3, and Z6. Those are the only possibilities, okay? And the analysis I was presenting here before with the saying that there's a particle of charge 1/3 and so on and so forth, okay? It's valid for the product form of the gauge group when you take this to be 1, okay? In cases where you take, so I think it's true where you take it to be 1 and Z2, I think it's also valid. It's not valid when you take Z3 and Z6. Why is that? Because once you work out what's the group after Higgsing, it's actually in the two, it's SU3 times U1 electromagnetic modulo can be modulo Z3. Okay, so this in these two cases can get a Z3. Okay. So what that means when you have a group like this is that when you have a quotient like this quotient can change the allowed representations. And what this thing does, this C3, it forces that it basically this Z3 is identifying the center. So this thing has a center, which is Z3. It's identifying the C3 here with the Z subgroup of here, and this is basically forcing that the two subgroups are correlated; they become the same, and that basically forces that something in the 3 of SO3 must have a charge which is divisible, which is a not it is a fractional number, so n is not multiple of 3, and it's forcing that anything that is a singlet has integer charge. Okay, so if the gauge group is this, okay, then we are not predicting this particle. We actually predict we predict that the spectrum of particles that we have observed already in the standard model coincides with what you predict from Swampland principles. So in this case, if this group is Z3 or Z6 and we don't know which is the correct choice, we wouldn't predict new electric particles. However, in this case, completeness principle, I will not explain the story in detail because it would take too much time. But in this case, completeness predicts monopoles, so magnetically charged objects of fractional magnetic charge. So monopoles we haven't observed, but we believe we have an idea of what their allowed charge, the allowed charges can be because of their quantization. And if the gauge group is either this or this, the charges of the monopoles, the quantization properties of monopole charges are different. Okay, so to sum up, Swampland, so the completeness principle, the completeness makes predictions for the standard model. But it's unfortunately, I wish I could give you like just a simple prediction, like it's gonna be a particle like that. It's a bit more complicated than like that. If there's 2 cases, then we get fractional electric charges. If in the other 2 cases, this is C3, then fractional magnetic charges. Okay, so this is the prediction of the completeness principle for the standard model. All of this in principle is observable. We're looking for monopoles, so we're going to be able to hopefully to see what the charge quantum of monopole is. And these particles, if they're very heavy, but they're produced electromagnetically, maybe you can see them in cosmology or produced in some other way. Okay, so this conjecture has concrete clear implications about beyond standard model of physics. They're connected to this interesting question, or what is the global form of standard model gauge group? This is a question which is not often discussed, which is why I wanted to bring it up. But before I go on, let me then stop and see if there's any other questions. Please ask anything. Again, as I was emphasizing yesterday, this works best the more questions you guys ask.
Excuse me.
Please.
Can you hear me?
Yes, I do. Thank you.
Does this completeness principles tell us something about the mass of these predicted particles?
You just asked the $1 million question. Great question. No, unfortunately not. And that is a bummer. That is a big bummer. That is something very unpleasant about completeness conjecture or global symmetry conjecture. They tell you something has to happen. They don't tell you which energy scale. So yesterday, you remember we were talking about B minus L is broken or gauge, but I was not telling you at which how weak the coupling was or how strong the breaking effects are. And here is the same. It's really the same because I'm putting these particles to break a one-form global symmetry, but their mass controls how strong the breaking is, and I cannot tell you what it is. So I think I don't know if she has talked about it today or she will do it tomorrow, but I think Irene is covering a different Swampland conjecture, which is the weak gravity conjecture. The weak gravity conjecture tries to address precisely this point. Okay, so from completeness of the spectrum, I cannot tell you what the mass of this charge is, but from weak gravity conjecture, I can. I can tell you that its mass is lower than the electromagnetic gauge coupling times m Planck times its electric charge, which is 1/3. So it's lower than this number. Now, in the real world, electromagnetic coupling is 0.1. So this mass is something like, being generous, something like 10 to the 17 or 10 to the 18 GeV. So it can be very heavy. Unfortunately, it can be very heavy. This I got using weak gravity conjecture. Okay, I didn't get from completeness of the spectrum. Did I answer your question?
Yes, thanks. And another relative question: can we expect that somehow we can see the fingerprints of these particles in the inflationary correlation functions?
This is a great question. So I'm not sure if in inflationary correlation functions, but people have discussed. So not directly this particle, I think, because we know very little about what the matter sector is during inflation. But this guy, what is the possibility, the value of gamma, okay, of the standard model gauge group, is related to some other things. So for instance, is related to the properties of cosmic strings. And there is a paper, which unfortunately I don't have with me right now, but I will make a note to bring it up tomorrow. There's a paper by Pratik Agrawal and collaborators in which they discuss observable signatures in the sky depending on the choice of gamma. They make some assumptions. One has to be lucky, so it's not guaranteed you will observe it, but it's possible. So perhaps it's best if you let me get back to this tomorrow, because I can give you the details of the paper.
Yeah, okay. Thank you very much.
Okay. So I made a note to bring this tomorrow to the lecture. Any other questions? Thanks. This is great. This is exactly what this is about, to ask questions. Okay, very good. So completeness principle, we just discussed one application for the standard model. But I'm a string theorist. I also care a lot about string theory itself. So one application of the completeness principle that I really like, and that has been this is pioneering work by Kumrun Bafa and collaborators 3 years ago, actually, is to use completeness to obtain, within quotes, string theory or strings. Let me just say strings, okay? So to argue there must be strings in the spectrum. Now, unfortunately, Kumrun and friends did not argue for this in the standard model. That would have been great to argue that you must have strings in the standard model, but they actually argued it in a different theory. So they were looking at a different quantum theory of gravity, which is supergravity, so the supersymmetric. I'm going to first describe 10 dimensions, although the argument is more general. It also works in any case with 16 supercharges. I'll maybe get back to that in more detail tomorrow. So let me first describe the setup they were asking, okay? So usually when we describe supergravity in 10 dimensions, so they were looking at the minimal supergravity you can have in 10 dimensions. So that's n equals 1. So that's 16 supercharges. Okay. So what is supersymmetry? So with supersymmetry is this symmetry in the action that you can have in a theory that relates bosons to fermions, and it gives you amazing control. And supersymmetry gives a lot of control on the theory, And if you consider a theory, the higher dimension you consider, the more control it gives you. There's a limit. There's a maximal dimension you can consider, which is 11. Because if you go beyond 11, the supersymmetry, just like any other symmetry, fields come in representations of supersymmetry. And for dimension bigger than 11, you have states that you cannot describe within effective field theory, simply in the multiplet of the graviton. The content of supergravity in 10 dimensions is with supersymmetry in 11 dimensions is fully fixed, and also in supergravity in 10 dimensions with n equals 2. But here I'm talking about a slightly different case, which is the minimal amount of supersymmetry that you can put in 11 dimensions, sorry, in 10 dimensions, which is what we call n equals 1, 16 supercharges. Okay. Usually these theories, when one talks about supergravity in 10 dimensions, one is usually assuming string theory. But this doesn't have to be the case. This is not the logical way to proceed. In fact, it's not even the historical way things happen. On one hand, you had the string theorists thinking about string theory. And on the other hand, there were people exploring supergravity theory with no direct connection to string theory. And they were figuring out these things as they go. So a supergravity person would be very interesting in supergravity theories in 10 dimensions with 10 supercharges, because even though they are very constrained, they are not completely constrained. Okay. So I told you that fields come in multiplets in supergravity. And it turns out with this much supersymmetry, life is very simple. There are just, with 16 supercharges, there are only 2 multiplets. There's the gravity multiplet, which, as you may guess, contains, I'm gonna write the field content of its multiplet. What are the fields it contains? It contains the metric, graviton. It contains a fermion, because supersymmetry relates both to fermions, it's called the gravitino. It also contains a scalar, which we call the dilaton. It's just a scalar there. Another fermion, the dilatino. And last but not least, what we call a B field. Just like the metric has 2 indices, mu nu, and it's symmetric, the B field is antisymmetric. Has 2 indices and it's antisymmetric. And it's a higher dimensional version of a gauge field. How do we see that? Well, for an ordinary gauge field, A mu, the field strength F mu nu is antisymmetric. If we have B mu nu and we take its field strength, which we typically call H, it has 3 indices, H mu nu rho, and it's fully antisymmetric. So its field strength behaves very much like a gauge field. And indeed, we will see that this is like a higher dimensional version of gauge field. Okay. The only other thing, any questions about the gravity multiplet? Okay, I am just describing the field content of 10D n equals 1 supergravity. Okay, I'm gonna set up this theory, and then I'm gonna show you how you can use Swampland principles to learn very information that you cannot get in any other way about it. So this is the gravity multiplet. The other multiplet that you can have with this supercharge is the vector multiplet. Now, the vector multiplet is much simpler. Has, you guessed it, a vector, A mu, and a fermion, gaugino, let me call it lambda tilde to distinguish from the other guy. And that's it. In 10 dimensions, that's it. That's all it has. Okay. And so when constructing a supergravity in 10 dimensions, you write a Lagrangian involving, so to construct Sugra, just write Lagrangian with the above ingredients. what are the ingredients one has? Well, this is like a recipe for cooking. You need to take this much of this much of that. So you can take one gravity multiplet because you want to have a theory of gravity, but you cannot take more than one because a theory with 2 or more gravitons, it's very difficult to make sense of it quantum mechanically. So let's just take one gravity multiplet, and then let's take some vector multiplets. How many? Well, we don't know. Take n vector multiplets. And you know, maybe these vector multiplets, they talk to each other, they're in an abelian gauge group. So actually they could be in an abelian gauge group G, okay? So for instance, if I want to get group G, I need dim of G multiplets, right? I need as many multiplets as I would require. So the dimension of G is the number of gluons there are, and I need to include as many gluons as I need to get the group G if I want to get group G. Any questions about this? Okay, so the nice thing is that once, when you're writing effective field theory from the standard model or any quantum field theory, you need to pick what are your fields, and then you need to write down the Lagrangian, and then you need to choose the couplings of the Lagrangian. There's many choices here. Here, that's different. Because of supersymmetry, the Lagrangian is fully specified once I choose number of multiplets and the gauge group G. Okay. Oh, there's a question. Can you repeat why do we choose just one gravity multiplet? Yeah, thanks for the question, Farhad. So the reason why we choose just one gravity multiplet is because, each multiplet contains a certain set of fields. So if I were to pick, I pick at least one gravity multiplet because I want to have a theory of gravity. So I want at least one graviton. So at least one gravity multiplet. If I were to pick 2 or more, okay, that would be a theory with bigravity, free gravity, for gravity. It will have many gravity multiplets. We don't really know how to write down consistent actions for those. Okay, certainly we don't know how to do it supersymmetrically, and the whole point here is about doing a supersymmetric theory. If we have a non-supersymmetric theory, then you can try and make sense of theories of 2 gravitons by doing tricks which in the end amount to making one of the combinations of the gravitons massive. So it's really not a massless graviton. And the basic reason, okay, one intuitive reason why it's difficult to make theories with 2 gravitons or more work is because of Einstein's equivalence principle. If you have a theory of gravity, it couples to all of stress energy, okay? So the coupling of gravity to matter is universal, it's G mu nu, T mu nu. If you have a second graviton, it also couples like G mu nu, T mu nu, okay? It's graviton 2. So when you add the 2 terms, in the end, it's just one thing that couples to T mu nu. There's no way to distinguish these 2 gravitons, right? There's just one there's one linear combination that couples to matter, and the other linear combination doesn't couple at all. So it's not physical. This is why it's very, very difficult. I would say it's impossible to make theories of gravity with more than one gravity multiplet, and why we certainly do this in this setup. I hope I answered your question, Farhad. If not, just let me know. Or also, okay, perfect. And also remember, if any questions come up at any other time, you can shoot me an email. I wrote my email on the first slide. I'm gonna put it again in case anybody wants to write. Okay. So just again, just write me if you have any questions about the lectures. You feel sometimes during the lecture, it's not the best time to have like a long discussion, right? If you feel like that, you can also send me an email whenever you like. Okay, very good. So this is the Lagrangian. It's fully specified once I choose this modulator G. And there's actually, and this is something specific to 10 dimensions. There's one more thing, one more restriction, which is a very powerful principle called anomaly cancellation. This is a quantum mechanical phenomenon. If you ask me personally, I think it's one of the most amazing, coolest things that you can find in quantum field theory or quantum gravity. Is really cool and very powerful. So what is anomaly cancellation? Anomaly cancellation happens when there is a symmetry. So an anomaly, roughly speaking, I mean, to give a full course about anomalies would take another set of 4 lectures. So I'm just gonna give you like the 1-minute pitch of what an anomaly is. What is an anomaly? An anomaly in some symmetry, it means that the symmetry is broken by quantum effects. And so if this symmetry is gauge, the symmetry, which is anomalous, is gauge, this is bad. It's very, very bad, because to gauge a symmetry, we need it to be an exact symmetry. We cannot gauge it if it's not exact. So you cannot have a gauge anomalous symmetry. So anomalies need to cancel. There's a principle. So there's a principle. Anomalies need to cancel. So when one studies the question of anomalies in 10D n equals 1 theories, so 10D n equals 1 SUSY theories have a lot of anomalies. This was studied in the 80s by Green, Short. Let me write that properly. Green, Short, and you can find it a very good discussion in the Green, Short, Witten book of string theory, superstring theory volume, superstring theory volume 2. Okay. So you can have a good discussion of that, but the upshot is that I told you that you could choose any gauge group G, but it's not true. If you to cancel anomalies, G has to be one of the following 4 possibilities. Okay, so these are all different gauge groups that are there. So E8 is the biggest exceptional Lie group. This is like SU2 or SU5, but more complicated. SO32 was just a rotation group in 32 dimensions. U1 is just the group U1. And so the point is that only these 4 possibilities, cancel anomalies in 10 dimensions. Okay. So just from field theory analysis, we know that the gauge group in 10 dimensions of gravity is completely fixed to be one of the 4 of these 4. Okay. Any questions so far? Okay, so the group is one of these 4, and here's the thing: these 2 appear in string theory. They are these two are they are realized, appear in string theory, which is to say there are known string compactifications, which are theories of gravity, including massive states and fully consistent, which at low energies look like their gauge group in the dimensions E8 cross E8 and SO32. Okay, so these are both heterotic string theories in 10 dimensions. But here's the big question. These other two, this one, do not. We don't know how to construct them as the low energy limit of a string theory. Okay. Now, this question that I'm telling you, the question of whether these two, of course, this leads to the natural question: are these two guys that you don't know how to get in string theory, are they really consistent? Maybe there's another way to get them in string theory. Maybe there's a different quantum theory of gravity other than string theory that realizes these guys, or maybe they're inconsistent. But this is a question, okay, that was open. This was realized already in the 80s when anomalies were canceled. And this question was open for roughly 30 years, okay, until a paper by Taylor and collaborators, I think it's the Wolf, Taylor, and it's a third author, I'm forgetting, from 2010, where they give an argument why these two possibilities have to be inconsistent. But what I want to tell you is how to. It's a more recent about a more recent piece of work, which is 1905-08261, which is by Kim, Xu, and Kurumbafa, where they argue that these two theories are in the Swampland, and they argue it purely from completeness principle. So U1 to 248 times E8, and U1 to 496, they're in the Swampland from completeness. Okay, so just the completeness principle becomes very, very powerful with this match supersymmetry in this high number of dimensions. Okay, so let me explain how the argument comes about, because it's very nice. Remember I told you somewhere over here that part of the as a consequence of supersymmetry, one of the fields that one has in 10 dimensions is this B field, which looks like an antisymmetric tensor. Okay, so it looks like an antisymmetric tensor in many ways. In particular, you can construct operators which are just like the Wilson lines that we were constructing before for gauge theory. We need to integrate over some surface. So this is B mu nu, and a surface has two tangent vectors, so it's n1 mu and 2 mu. But you can define these operators, which are something you could call them like Wilson surfaces for charge Q, or depending on the surface sigma. We can construct these operators. Okay, they are the same as the Wilson lines in electromagnetism, but for these two symmetric tensors. And so completeness says they must be able to end. What do they end on? Well, this is a surface operator, okay? So when they end, what do they end on? They end in they basically end on a string. They end on operators. So you have remember, so before for the electromagnetic theory, we had a line that ended on a local operator. And that local operator was creating a charged particle. What you have here is a surface. Surface and surface, sigma. And so on a line operator. And this line operator creates a string. Okay? So bottom line here is that completeness principle, let me just write this big because it's important. Completeness applied to the B field leads to the existence of strings. Okay. Now, what we've done is in a theory in 10 dimensions with distinct supercharges, just by applying completeness, we conclude there has to be strings on the spectrum. The strings will have some tension. We don't know what the tension is. We cannot see it from the massless effective field theory, okay, from the massless level, but certainly there are strings on the spectrum, and we just learned this from completeness principle. Now, when I ask what the strings are, for instance, in these two examples in heterotic string theory, well, of course, this is just the fundamental string we know and love. But the power of the completeness principle is that it tells us there's a string even in these other two cases that we don't really understand. Okay, even in these two cases, there has to be a string. And so we can learn things by studying the physics of the string. So the next thing I'm gonna do, I'm gonna draw one such string, one long string. I know it exists because of completeness principle. So this is a string. And I'm gonna study the physics of its work volume. But before I do that, let me pause and see if there's any questions about any of this. Okay, it's a bit formal, but the basic idea is there is a choice of gauge group when constructing supergravities in 10 dimensions. And there's two choices that we know appear in string theory. There's other two choices that we don't know how to construct in string theory, and we are trying to understand if these theories are in the Swampland. So there's a question by Tolga. Let me see. These strings are BPS. Very good. Very good. So this is completely correct. Yes. So actually, exactly. So I didn't say from the completeness principle alone. Okay, you do not get that the strings have to be BPS. They don't have to be. I mean, the completeness principle doesn't tell you this. But in theories with supersymmetry, with enough supersymmetry, it's certainly always true that the objects that satisfy the completeness principle are supersymmetric objects. And in fact, you're completely right. I'm going to assume that the string is BPS. What does it mean for those of you that are not familiar with notation? What does it mean that the string is BPS? Well, just like for any symmetry, you can some symmetry group which is preserved by the vacuum. Subgroups of the group can be preserved by different objects. Saying that it's BPS means that it preserves. It's a configuration that preserves some supersymmetry. So the algebra, the supersymmetry algebra in 10D n equals 1 has 16 supercharges, and the string I'm talking about is going to preserve. The only possibility really is that it preserves 8 supercharges. So it's what we call half BPS. Okay. Well, depending on who you ask, some people might call this just full BPS, and then or supercharges half BPS. Yeah, let me just remove this. It's just BPS. Okay. Did I answer your question, Tolga? Yes, these strings are BPS. Okay. So let me just put here. Strings are BPS. Okay, good.
Sorry.
Yes, please.
These strings are not dynamical, are they?
Very good question. Okay, the strings are dynamic. in the same way that when we have, in the other case, we have the line and the line ends on local operators, or we predict particles, and the particles are dynamical. The strings that we predict here are dynamical. However, here's the thing. If there's a dynamical string in the theory, that can wiggle around, can be, you should in principle quantize it, do string perturbation theory with it. That's very complicated. I'm not going to be able to do that right now. But one thing I am allowed to do actually is to consider one particular state of this dynamical string where the string becomes very, very, very long. Still dynamical, okay, but I am making it to be very long, to have infinite energy. And so when I make that and I make it infinitely long, the string is dynamical, but its dynamics are very constrained. In fact, for this string, about the only thing that can happen is that, because it's infinitely long and stressed, the only thing that can happen is that it wiggles a little bit like this. It can wiggle like this, it can wiggle like that. So there's a theory for the fluctuations of the string. So there's just a word there's a word volume theory. So there's just a word volume theory that describes fluctuations of the string around its equilibrium position. So the string is dynamical in this sense, it can wiggle around, okay? But you're right that because I made the string very, very long, I basically made it infinite, it cannot wrap up by itself or, do all sorts of funky things that were used from perturbative strings, because for perturbative strings, we usually quantize closed strings. This is kind of like a string that I made very, very large, and then I just look at one part of it, and then I just allow wiggles like this. Did I answer your question, Ali?
Yeah.
Okay.
And you just added them to not have a global symmetry like the thing you did yesterday?
Exactly. It's a 2 from global symmetry coming from the P field as opposed to a 1 from global symmetry coming from the A field in the other case. That's exactly right. That's correct.
Okay.
Okay, good.
So
So we have this. Is there any question?
Yes.
Yeah, please, Madis.
This is kind of funny because for the case of strings and all the other extended objects, we have kind of completeness built in. We have all the possible charges because they can vibrate and they support all the possible nth charge. It's not the case for point particles, right?
Is that the case for what? For
zero branes, point particles.
Right. So I don't think we know from the get-go in any circumstance that we have all the charges. So for instance, I think correct me if I'm wrong. So just to see if I understood what you were saying. You're saying that, for instance, when I have a string, I can quantize the string worship and I get that full spectrum just by quantizing the perturbative string, right? The perturbative string theory, I get the full. That is absolutely right, of course. But it's not. That's an argument that is not universal. Works for some fields. So, for instance, if you do this in type 2A string theory, it will work for instance, winding or momentum U1s that you can see in the worksheet. It will not work for Ramon guys. Ramon guys, you cannot argue from this. You need to argue in some other way, right? And furthermore, so already in string theories, as the example I'm giving you shows, it doesn't work in general. Although look, it can be very useful. In that corner is a huge corner where you can just prove completeness from the worksheet, which is completely right. But here, you see, what I'm trying to do here, I'm trying to say that this string exists. Also, for any quantum theory of gravity, I'm trying to understand if these two theories are in the landscape or in the swampland. And so I just argued there's a string. I cannot assume that I can do string perturbation theory with it. Maybe it's a string, but it's not perturbative. I mean, or the rules are different. If I assume string perturbation theory, I can do a worksheet proof that these two things do not exist, but it wouldn't be a swampland proof. The whole point of swampland is trying to get things from general principles, right? And so what I'm only going to assume is indeed there's this string. And so I'm going to assume this string, that there's BPS, and I told you anomalies were very powerful. I'm also going to assume something called anomaly inflow. Now, this is a very powerful technique. It's very technical, has to do with anomalies. So I'm not gonna give the details of this. If people are interested, I can provide references. But or the paper, actually, the paper I cite here, the one basically I'm reviewing the results of this paper. So this paper contains a very good introduction to anomaly inflow. Anyway, the basic idea of anomaly inflow is that when you have a string here embedded into some ambient space, a string is ambient, some properties of the ambient leak into the string. Okay, so let me now explain what these people did. Okay, let's look at the theory that I was describing here, the theory of the fluctuations of the string at very low energies. What kind of theory is it? Well, string theory has 1 + 1 dimensional world volume. So it's a 1 + 1 dimensional theory describing fluctuations. And, you know, in quantum field theory, we often have theories which have scales, right? We have like the mass of the electron, whatever. Suppose that we are interested here in just describing the low, very, very, very low energy fluctuations of this string, okay? So if there's any energy scale, you give me this, oh, there's a special energy scale, that's like the string tension. No. We want to understand what is the physics much below the string tension. If there's some other energy scale which is special, no. We want to understand what is the physics much below that energy scale. So if you keep doing that game, you keep asking what is the IR limit, the deep, low, long wavelengths, low energies, IR limit of the world volume theory of the string, you reach one conclusion. It has to be a theory without scales. And that is what we call a conformal field theory. There is a lot of techniques, a lot of that we can learn from conformal field theories, okay? And in particular, this will not just be a conformal field theory, because the theory is supersymmetric. It will be what we call a 0,8. Never mind that, it's just it's a way to encode the supercharges that we're preserving. Is a 0,8 super conformal field theory. We know a lot about these guys. And in particular, let me make a very long story short. There is a certain quantity, which we call CL, the left moving central charge, is a quantity that exists in any CFT. And this quantity, because of anomaly inflow, okay, we know on one hand, because of anomaly inflow, the unitarity condition of the string, we know that it's lower than 16. And we also know that CL is bigger or equal than a certain sum involving some numbers. Let me just, I'm going to explain what this is momentarily. So we know these two things. We know that the central charge is upper bounded by 16, and we know that the central charge is lower bounded by a sum involving some things, which are here. This is the dimension. This guy, this guy is the dimension of the space-time group. This is what I told you, that anomaly inflow allows you to learn to see properties of the ambient. So the ambient has some gauge group G here, and anomaly inflow. So for instance, this gauge group maybe has a parallel factor. So it has G1 times G2 times blah, so many things. So to each of these factors, I'm going to call GI. And the dimension of this GI appears in this lower bound for the central charge. And then there is these numbers are the dual cosector numbers of the algebra. They're just tabulated. So for instance, for E8 it's just 31, and for SO32 is actually also 31. You know, some numbers that you can tabulate, mathematicians computed them. And these numbers are called the level of the current algebra. In principle, we don't know what these integers are, but also because of inflow and unitarity, we know that in this case, the KIs are exactly equal to 1. Okay, so actually, we can write down a bound. 16 bigger than C left, bigger than sum of dimension of GI, so over every I, times HI. Okay, we can write this bound. And so one thing I can do if I want I could just forget about this and just move this like this. Just take this and move it here. So here's a bound. From anomaly inflow and the existence of this string, which I infer from completeness principle, I get an upper bound involving the dimensions of the gauge group and their Coxeter number. Sorry, these levels are 1, so I should have, this is H1 plus 1. Okay, so let's see if this bound is satisfied. For E8 cross E8, I have 2 terms. Each of the term is, the dimension of E8 is 248, and HE8 nu plus 1 is 32. So for E8, this bound is 16, bigger than or equal to, there's 2 factors of E8, so there's 248 over 32 plus 248 over 32, and that is exactly equal to 16. So it's saturated. Very good, E8 cross E8. For SO32, there's just 1 factor. The Coxeter number is the same, so it's just 16 is lower than 496 over 32, which is 16, so it's all satisfied. So the 2 string theories that we know and love saturate this bound. But now we argue this bound as a Swampland principle. It must hold in general. So we can apply it to E8 times U1 to the 248. Well, let's see. Let's see then. So that's 16. And the important thing is that for a U1, the number for U1 is just it's actually 0. So there's just a 1. So it has to be 16 is bigger than 248 over 32. This is coming from the E8 factor plus 248. Can anybody tell me if this equation is verified? Is it satisfied? No, it's not. This is bigger than 16. So this theory is in the Swampland. And for the U1 and 496, is also not satisfying. So it's also in the Swampland. So by using completeness, we are able to show that these 2 theories are in the Swampland. And so to wrap up for today, I will just say that out of these 4 possibilities, these were the 4 possibilities that existed in 10 dimensions. And now we have understood there's just the 2 of them that are okay with Swampland principles are precisely the ones realizing string theory. In other words, in 10 dimensions, everything that is consistent with Swampland principles is the lower energy limit of a string theory. So we have realized in 10 dimensions what you might call, what people call sometimes string universality, or the string Lampos principle. Every theory, 10D theory, every consistent is the low energy limit of string theory. So for 4 dimensions, we can still have the question whether string theory is the only quantum theory of gravity. But in 10 dimensions, we don't. Every quantum theory of gravity looks at low energies like a string theory. So that marks the end of the lecture for today. What we will do tomorrow is we will extend this picture to lower dimensions. Also, so we also have string universality also in 9 dimensions, 8 dimensions, 7 dimensions. Well, in 7 dimensions, we don't have it, but almost. And this is some very recent results on which I've worked, and also Kunrum and other people. And they are the way you argue, these are very recent results. The way you argue universality also for 9 and 8 dimensions, you must use a different Swampland conjecture, which is called the covariance conjecture, which is what I will explain tomorrow. I am very sorry I was a bit over time. I hope this is still time for 1 or 2 questions, if there's any.
Thanks, Miguel. Very nice. Enjoyed it. There are time for questions. Yes, there is 1 question, please.
Thank you. So I was just making a guess that maybe if you have a higher dimension about the big gravity conjecture bound on the mass of the possible particle. So if you have a higher dimensional gravity theory and we supposing we live on a brane, so